All right, so now we have section 4.4, derivatives of exponential functions. Derivatives of exponential functions are their own little special little subcategory of derivatives. They don't normally follow the same rules as we've seen before in other functions. So for exponentials, the derivative of e to the x is e to the x. So they're special. We'll see when we start talking about rule number 2 in a second, we'll see why that's true. So the derivative of a to the x, so for any exponential function a to the x, the derivative is the natural log of our base a times the original a to the x. So it doesn't matter what we have, 5 to the x. It's ln 5 times 5 to the x. Derivative, so for our second case here, derivative of e raised to some function g of x. So we just talked about that the derivative of e to the x was e to the x. So now let's dig in and see why that's true. So the derivative of e raised to g of x, its derivative is e raised to the g of x times the derivative of our exponent. So if we go back to e to the x, well, the derivative of x is 1. So that makes perfect sense based off of this new definition here. Same thing for a raised to some function g of x. Its derivative is the natural log of our base a times a raised to the g of x times the derivative of that exponent. So we're still doing the same thing. Again, up there for a to the x, the derivative of x was 1. So that was a simplified case of what we were already looking at. So that's kind of what's going on there. So let's work through some examples and see what we have here. So if we're given y equals e raised to the 3x, that would mean its derivative is, by rule number 2, it's the derivative of my exponent. So derivative of 3x is 3 times my original function e to the 3x. Every time when you take the derivative of an exponential, you will have your original exponential in there with nothing done to it every single time. If we have something that's out front, it doesn't change anything. So y prime, so the derivative of minus 5, so we'd have minus 4 times the derivative of minus 5x is minus 5 e raised to the minus 5x. Simplifying, we would have 20 e to the minus 5x as our derivative here. So what if we have functions that are added to it? Does it change anything? No, it doesn't change anything whatsoever. So the derivative of our exponent 3x squared is 6x e to the 3x squared. Derivative of plus x is just plus 1. So that would be our derivative here. If we look at the next one, it's a product rule. So y prime equals, we've got 6x squared, and we get e to the 3x as our two functions. So the derivative of the first is 12x e to the 3x plus 6x squared times the derivative of e to the 3x is 3e to the 3x. If we wanted to simplify this, 12x e to the 3x plus 18x squared e to the 3x. We could simplify this further. We could, in fact, pull out a 6x e to the 3x to make this 2 plus 3x in parentheses here. It all just depends on what the problem is asking us to do, on if that is the best thing or not. Again, here, same thing. We can use the chain rule along with the product rule. So here's our product rule. So this is 4 times x plus 1 to the third times 1 times the original of the second plus the original of the first times the derivative of the second, 6e to the minus 6x. If we want to simplify this, we could pull out, excuse me, we could pull out a 2 times x plus 1 to the third e to the minus 6x. And we'd be left with 2 plus, actually, 2 plus parentheses x plus 1 times -3. So it would be 2 times x plus 1 to the third e to the minus 6x times 2 plus, sorry, not plus, minus 3x minus 3. So you get 2 times x plus 1 to the third e to the minus 6x times -3x minus 1. So it all just depends on what we're doing, because that will determine which one is best in terms of which way we want to do things. We could also have quotient rule. So y prime equals low, so 2e to the x minus 1 times the derivative of the top, which is 5e to the x. So low d high minus high times the derivative of the bottom, which is just 2e to the x, over the bottom squared, 2e to the x minus 1 all squared. If we simplify that, we get 10e to the 2x minus 5e to the x minus 10e to the 2x over 2e to the x minus 1 all squared, which would simplify down to minus 5e to the x over 2e to the x minus 1 all squared would be our derivative using the quotient rule. If we had just an exponent here, so our exponent, remember what our rule told us, it said a raised to the gx is natural log of the base times the function times the derivative of the exponent. So this is going to be ln of 3 times 3 raised to the minus 3x times -3. If you wanted to rewrite that, minus 3 ln of 3 times 3 raised to the minus 3x, you could, no worries at all. Again, y equals e to the x minus e to the negative x over x using the quotient rule. Y prime equals low times the derivative of the top is e to the x plus e to the negative x minus the top, which is e to the x minus e to the negative x times the derivative of the bottom, which is 1 over the bottom squared. So not a lot of simplification you can do here. X e to the x plus x e to the negative x minus e to the x plus e to the negative x all over x squared. That's about all we can do with that one. So we're told, suppose S of t is equal to 120 minus 70 e to the minus 0.2 t. What's the rate of change at t equals 5? So all we need to do is find our derivative. S prime of t is minus 70 times negative 0.2 e to the negative 0.2 t. So negative 70 times negative 0.2 will give me 14 e to the negative 0.2 t. Next, we need to plug in t equals 5. So S prime at 5 is 14e to the negative 0.2 times 5. Plugging all this into our calculator at 1 point. So 14e to the negative 0.2 times 5 is 5.15 if we round to 2 decimal places. Keep in mind, whenever we're doing this e function, if you're using since you have to use the TI-30X2S, you would need to, in your calculator, when it opens up this big parentheses, type in the negative 0.2 times 5 in your parentheses. Otherwise, you're going to get a different answer.
Yeah.
So make sure that's kind of what we're doing when we're taking derivatives of exponentials.